In this lecture, we talk about Grothendieck spectral sequence. So let A, B, C be abelian categories, and these categories have enough injectives. So that means you're given an object in this category or any of these three categories, you can form their injective resolutions. So F and G be left exact covariant functors. So F takes objects of category A to category B, and G takes the object of category B to category C. Now F and G are left exact covariant functors, so we can take their right derived functors. So this I have explained in the lecture on balancing Ext. So this lecture, balancing Ext, is extremely important to understand Grothendieck spectral sequence, because the ideas from this lecture, which are very concrete, are used in this lecture on Grothendieck spectral sequence abstractly. So these right derived functors, which were Ext functors, we had Xn here. So instead of that, we are saying now we have RPG and RQF. So right derived functor of functor G, this is right derived functor of functor F. So now we can also take right derived functor of the composition. So composition, you first apply F, you land in B, then you apply G, you land in C. So this composition goes from category A to category C, and then you can form the right derived functor of this R and GF. Now the Grothendieck spectral sequence encodes the relationship between the composition, so that is between this and these individual functors. So and the individual functors, and the secret sauce is fully injective resolution, or as in the previous lecture we called it Cartan-Eilenberg resolution. So if you know the lecture on balancing Ext and the lecture on Cartan-Eilenberg resolution, then you are good to go, because both these lectures actually concretely discuss what we are going to abstractly say in this lecture. So these two things are related to each other, and that is what is Grothendieck spectral sequence. So now we come to the theorem about Grothendieck spectral sequence. So say you have an A, which is an object in category A, and then you can form its injective resolution like this, a complex. So just like we formed one in the lecture on balancing Ext, and you apply this functor F to it. So if you once you apply functor F to it, you are now working in category B, and we suppose that this is G acyclic. So that is right derived functors are 0 for n greater than 0. So again, we had a concrete notion of this for Xn. So in the lecture on balancing Ext, we put this Xn as 0 for n greater than 0, and that formed a crucial piece for balancing Ext. Similarly here, this is going to form a crucial piece. So again, it is advised that you see this lecture balancing Ext if you really want to understand this more concretely. So then for each A which is object in this category A, we have a spectral sequence. The page 2 looks like this. You have the right derived functor of G composed with right derived functor of F, and this A object is here. So this A object has a resolution like this, and the page infinity just looks like this, RP plus Q composition. This, so you are relating these two are coming right here, and derived functor this is coming right here. So let us see this in more detail, and now we start proving it. So start with working in categories B and C. So say this is category B, this is category B. So you have our complex, this A, and you apply functor F to it. So you get FA0, FA1, FA2. Again, we applied the functor home here when we were discussing lecture balancing Ext. And then you take injective resolution like this. So for FA1, again take injective resolution like this. FA2, you take injective resolution like this. So this resolution is essentially the fully injective resolution, or this Cartan-Eilenberg resolution. So after you do this, you drop this. So you drop this, and instead of this you put zeros. So this is exactly what we did again in balancing Ext, so that when you take vertical filtration and start computing cohomology, then everything here will be 0 because of this acyclicity, and at the 0th place you will have these things living there when you compute the cohomology for the vertical filtration. Again, exactly what we did in balancing Ext, but there we use the home functor, here we are just using any general functor f. So once you have dropped this, then you can apply the functor g to it and land in category C. So you're just putting g in front of everything here. So you have g, I1, I2, this thing. So you can see in front of this, you're just putting in g's. So you get this complex in category C. So once we have this, let us now start computing the cohomology using vertical filtration. So let us start with page 0 for vertical filtration, and what we are going to get is exactly this. So you're going to get this term. So now focus on the vertical filtration. So we have just taken the vertical filtration or the column filtration, and you assume that FAI are G acyclic. So that means if you take the right derived functors of this, everything is going to be 0 for greater than 0. So the only thing which survives is on the 0th row. So on this row something will survive, everything else will be 0. So again, this was done in the same lecture which is called balancing X more concretely, and this is what we have to show. So we are going to show this thing in this page. So this is page 0. So for page 0, we have seen before arrows go up. So we start computing the derived functors or computing the cohomology, which is essentially called the derived functors here. So again, these are 0 for greater than 0. So all these are going to be 0. And here, what is going to survive is exactly the term we dropped as in balancing X. So now we come to page 1. So notice that this I00, I01, etc. these were all injective resolutions of FA0, and then we are applying G to it. So again here, this was injective resolution of this FA1, you apply G to it, and this was injective resolution of this FA2. So again you have this, so page 1, so you can see the arrows are going one right. So again you take the derived functors of this. Now you start computing cohomology here. So here you will get the R0 term, here you will get the R1 term, here you will get the R2 term of the complex. So the way to write it is R0 of GF of A complex. So because when you write derived functors, you consider this entire complex. So you have this entire complex which is GF this. So you get R0 GFA, R1 GFA, R2 GFA, and everywhere else you have zeros. Everywhere else you have zeros. So this is our page 2. So on page 2, we have achieved convergence. So this will be also same as page infinity, because everything is 0 and the arrows are going to go like this and then land in 0. So therefore this is how page infinity looks like. And so you see this right derived functor. So this A complex actually comes from this object A. So you write it as R whatever this is, N G F A, and that is what it is here, RP plus Q GFA. So this P plus Q is N, because when you look at a spectral sequence, you look at the terms in the entire diagonal. So the entire diagonal terms will give you the cohomology, and here the only term living is here. So you generally take P plus Q for the entire diagonal. So only living term is here. So this is what is this portion. So this portion is done. Now we have to find this portion of the proof. So we have already shown this thing. This is what lives on page infinity. So now we have to show that page 2 looks like this. So for this we will take row filtration for page 0. So again we are taking row filtration. Notice that we have transposed the rows. So if you do not transpose the rows, you cannot fit it into page 0. So this is essentially page 0, and we have transposed the rows to fit in here. So once you have page 0, then you start computing the cohomology for page 1. And once you compute cohomology, this is also called the right derived functor. Again, this entire thing was shown on the lecture on Cartan-Eilenberg resolution. So where we showed that this how this cohomology was computed for the injective resolution for the rows. So we saw how the row and the columns gave us the same solution. So this was done in Cartan-Eilenberg resolution, so you have to see that lecture to properly understand what we are going to do here. So again, G is some appropriate functor so that it will commute with the cohomology of this. So G is just like the right kind of functor we have chosen essentially. So again, this is what our page 0 is. So you start taking the derived functors. So I'm writing R0. This is not the correct notation. So you compute cohomology here. You write it as R0 GI00. Here you write R1, R2. This is not the correct notation, but it gives you an idea that I'm computing the cohomology here, writing it right here. Cohomology here, writing it R1 here. Cohomology here, which is writing it R2 here. Similarly here. So generally when you write this R0, you write it for the entire complex. So here we have made assumptions on G so that it commutes with the cohomology. So basically you can take this inside. You can take this R1 inside. You commute it with G. So this you commute with G, commute with G, commute it. So commute it and then again commute it. So now so this is not correct notation, but it is very instructive to see what's going on. Now we come to the correct notation. So because when you say R0, you take it for the complex. So now we are taking R0 inside for the entire complex. So this I00, I10, I20, this was just a resolution of FA0. So this is what comes through. So instead of this, correct way to write is this after commuting. So again here, correct way to write is like this. So you have G of R0 of FA1, because this I01, I11, I20, if you forget about G, this is just the injective resolution of this FA1. So this comes right here. This comes right here. So again this is the injective resolution of FA2, and this R0 goes inside. And this is our page 1. So notice that page 1 you go 1 right. So now we will take derived functor of this. So for derived functor of this, the proper way to do it is that you think of it as a complex. So this is a complex of, because this A0, A1, A2, they all come from this complex A. So you take the derived functor, so this is what you get. So now you compute cohomology here for these things, and you get R0 here, GR2 for the complex, R1 here, everything else is the same. So instead of A1 we are writing the complex. Here you're writing the complex. So essentially it is just computing the cohomology group here. The cohomology group here, you write it like this. So this is just a chain complex. You compute the cohomology here, you write it like this. You compute the cohomology here, you write it like this. You compute the cohomology here, you write it like this. So notice that the cohomology was a functor which acts on our this chain complex and just gives you the cohomology group which corresponds to this. So this cohomology, so basically takes a chain complex into groups. So that is the meaning of the cohomology. So this is what you get. So now this is our page 2. So at 0, 0 you have this. So again this is our H1, obviously, because this 1 plus 0 is 1, 0 plus 1 is 1. This is our H2. So you have 2 plus 0, 1 plus 1, 0 plus 2, and so on. So this is our page 2. So you have exactly what we wanted. So write derived functor of G. So write derived functor of G, then write derived functor of F, write derived functor of F. So instead of A complex we are writing A, whose resolution we took to get this complex. And this gives you this thing right here. So again, the secret sauce here to properly understand this, that why can you do this, take the row filtration and then commute with the right derived functor. You have to see the lecture on Cartan-Eilenberg resolution and see how the row filtration gives you the same thing as you get in the column filtration. And that is what the Grothendieck spectral sequence is. The Grothendieck spectral sequence is essentially combining two concrete previous lectures. So one is Carta and Eilenberg resolution, and the second is balancing X. So both of them are combined together in the Grothendieck spectral sequence. You get infinity page immediately using this. So infinity page we got through column filtration or vertical filtration immediately. Page 2 we get from here. So this is very useful because it kind of abstracts a large number of other spectral sequences.